Hello everyone, my name is Yonglong Lin. I come from Zhongshan Medical University. Today I'm going to give a presentation of our paper, Laryngoscopy Object Indicators Analysis, based on MAX-RCNN. My presentation is divided into 4 parts, including introduction, method, result, and conclusion. And I'll start from the first part, introduction. In current otolaryngology clinical practice, patients come to see a doctor for vocal problems or throat discomfort. Otolaryngologists will take a preliminary diagnosis through the laryngoscopies. Laryngoscopies are to observe the pathology of the larynx, vocal folds vibrations, and the diversification in the glottal regions. The normal larynx is shown as the left figure. Some vocal tissues will be judged from the appearance of the vocal folds, such as nodules, laryngeal cancer, or glottal insufficiency, and so on. The vocal fold nodules and incomplete closure of glottal are shown as the middle and right figures respectively. Also, the diversification in the glottal region represents the movement ability of the vocal fold tissues. For example, to reflect the vocal conditions of the patient, or the glottal insufficiency caused by vocal fold paralysis. However, owing to the difference of vocal fold tissues in minutiae, diversity of lesion appearance, and the limited visibility of human eyes to recognize dynamic objects, there is still need for otolaryngologists to be assisted by the additional instruments to diagnose accurately. Therefore, the main purpose in this research is to analyze laryngoscopy videos with MAX-RCNN deep learning algorithm for segmenting vocal folds and glottal regions. These segmented objects will then be measured by different indicators so as to assist otolaryngologists with precise and efficient medical information in clinical practice. In this section, we will introduce the methods we utilize, including the laryngoscopy image dataset, data augmentation, annotation of data, architecture of MAX-RCNN, as well as self-built indicators calculation algorithm in this research. The figure shows the overall process of this paper. Next, the dataset used in this research is obtained from multiple sources, including the Department of Otorhinolaryngology, Head and Neck Surgery, Taichung Veterans General Hospital, public video stroboscopy dataset provided by Quantitative Laryngoscopy, as well as some laryngeal videos on YouTube. Here we collected a total of 45 videos and used 40 of them for training and the rest for testing. In order to avoid our model becoming overtrained by those high similarities among the adjacent frames in videos, we cropped each video into images with a rate of 1 frame per second, and got a total of 2,214 images cropped from the 40 training videos. Moreover, we augment the training data by adjusting the contrast and sharpening at different degrees. After augmentation, the training data set is expanded to 19,926 images. Then, the architecture of the MAX-RCNN network we utilize is shown as the figure. As we have known, MAX-RCNN is an instant segmentation deep learning model, and its architecture can be divided into 2 parts, before obtaining the proposal and after obtaining the proposal. The part before obtaining proposals could be further divided into backbone network and region proposal network, RPN. The backbone network consists of ResNet 101 and feature pyramid network, FPN, which are used for feature extraction of laryngoscopy images and output feature maps. The feature maps will then be input into RPN to detect objects, such as vocal folds and glottal, to find out the coordinates and locations of possible objects, which is inferred as proposals. After capturing proposals, the proposals and its corresponding feature maps will fine-tune the proposal's area through the part of ROI align. In the next step, the proposals will go through the fully connected layer to perform pixel-wise classification and coordinate adjustment. Eventually, the MAX-RCNN model will output the object with class and its coordinate. As for segmenting and labeling vocal folds and glottal regions, it is required to use FCN and ResNet 101 to output the images of the segmented objects. After we obtain the segmented vocal folds and glottal objects from max-RCNN, we then take them to calculate the corresponding indicators for each frame. There are 6 types of indicators shown as follows, which have been proved effective for evaluating the conditions of laryngeal lesions in many researches. Among these indicators, all of them are proposed based on the symmetric characteristic from the appearance and the movement pattern of the larynx. According to the symmetry of the vocal folds, we propose the deviation of vocal folds area, the deviation of vocal folds depth, as well as the curvature of left and right vocal folds. As for the indicators related to the movement pattern of vocal fold oscillations, there are glottal areas, glottal angles, and the triangles formed by the vertex of vocal folds. In the next section, I'll show out the training results of our research. Firstly, at the phase of testing, we used a total of 1,538 laryngoscopy images from non-training videos as the test data for the model. The confusion matrix of each class without data augmentation is shown as the left table, and the one with data augmentation is shown as the right. In addition, due to the high similarity among the surrounding tissues of the larynx, the vocal folds, and the glottal regions, we take background as a class within the confusion matrix represented as a class of segmenting failure. According to the confusion matrices in both tables, the numbers along with the diagonal side are representative of the fact that the model with data augmentation performs better in segmentation. Next, we calculate the average precision of each class and shown as the diagram. You can find that the model with data augmentation could significantly achieve better performance than the one without data augmentation. Hence, we adopt the model with data augmentation as the basis of the indicators analysis. We also visualize the indicators by labeling each type on the testing images, which can prove that our method could adapt different kinds of imaging conditions. In the last part, we've come to the conclusion. In this research, in order to analyze the laryngoscopy video, we propose to use max-RCNN model for segmenting the vocal folds and the glottal regions. Besides, we develop a self-built algorithm for analyzing the indicators, and visualize these indicators to provide objective medical information for otolaryngologists. Hopefully, with these accurate indicators from this research, otolaryngologists could diagnose more precisely in the clinical practice. Above is my presentation of this paper. Thanks for your attention.